Hi everyone, thanks for watching this video. So this is a video of part of a series, my thoughts on statistical issues. Because this is my first video, so I want to quickly introduce myself. So I'm a researcher. I have a PhD in econometrics. For recent years, I've been involved in research in health context. So I'm doing data analysis, modeling, etc. In the context of healthcare, or medical works. So today I would like to talk about the diagnostic testing, including sensitivity, specificity, PPV, and PV, etc., and the Bayes theorem. So let me start. So the motivation of my today's talk is these two tweets. So as you can see that it's talking about tests for COVID-19. So I don't need to say anything more about COVID-19, right? So this is the most important issue for the world right now. So we are right in the middle of pandemic, or at the end of pandemic, depending on which country you are in. So there are various tests. So there's tests for COVID-19 itself. There's also so-called antibody test. Okay, this tweet said the FDA has approved a test which has a very high sensitivity, more than 93%, high specificity, more than 95%. Sounds great, right? So for those who don't know what is sensitivity, so sensitivity is a true positive rate. Specificity is a true negative rate. So we are going to revisit these two terms later. Okay, so this is another similar twist. So antibody tests are coming. So it's critical to understand the implication, to understand the test. So if you are tested positive, if the test result says you are positive, so in this particular case immune, then how likely that you are truly immune for the virus. So this is very important, obviously. So if a test says you are immune to the virus, but then if this is false, then you're going to get infected, right? So this is quite that would be a very bad result. Let's look at this fundamental table. So I already mentioned that sensitivity is something called true positive rate. Specificity is true negative rate. So if we look at this, so I have to say, declare this is a table from Wikipedia. So they have this really nice table. Suppose you have this is a 2x2 table. So let me 2x2 table. Okay. So let's say the true condition has two scenarios. So if you're either truly immune, for example, truly immune, or you are not immune. So you're either immune or you're not immune. So this is called predict. On the column, you have this predicted condition. Right. So it's a general term. So in stats, when you say predicted condition, it could be it doesn't necessarily mean that something forecasting, or it could be mean that a test results. For example, you have this antibody test and you test it, whether it's positive or negative. So effectively, this test kit is predicting whether you are immune or not, right? So that's a term predicted condition is. So the test result could predict you are positive, or could predict you are negative. So if you are both truly positive. If you are positive and the test result also says you are positive, then this is called true positive. Otherwise, this is true negative. So this cell is true negative. So this, as you can see, this table is a bit complicated, right? There are so many things. So I have simplified this table, the previous table. So we don't need so many metrics, so many numbers. So this is a more simplified version of the previous table. As I said, there's true positive, true negative, false positive. Likely there's corresponding there's false positive and false negative. So here we see that this sensitivity, right? So this sensitivity is also called true positive rate. So it is the number of true positive divided number of condition positive. So this true positive rate is number of this cell and the sum of these two cells, right? So likewise, you can define this specificity, which is true negative rate. Okay, this is a true negative rate. So people using different terms in different contexts or different subjects. So basically, this is just another name. Sensitivity and is true positive rate. Specificity is true negative rate. So on the right hand side, you have this PPV, positive predictive value, and the negative predictive value. So likewise, true positive, this PPV is the this cell, number of this cell divided by the sum of these rows. True positive, number of true positive divided by out of predicted positive. Right. So this is a as I said, this is a fundamental table we're going to use. So now let's go back to the question. So the question is how likely you are immune to COVID-19, right? So we just discussed sensitivity and specificity, right? So the true positive rate and true negative rate, which both very high. True positive rate, true negative rate sounds great, right? But it's not really that straightforward. So now if we think about this test, the test has very high true positive rate and true negative rate. So what is effective says is if I'm immune, how likely the test show I'm immune. So if I written in this more mathematical way, it is a probability of test given test positive given you are positive, right? So this vertical bar is conditional, probability of conditional on this condition. So yeah, so in a word, as I say, is probability of test positive given that you are positive, right? If you look at the previous table, that's what is the true positive rate. That's the definition of true positive rate, right? So that's the test positive given you are positive, right? Now, but okay, let me get this done. So, but we are not really interested in this, right? What we are really interested is PPV, the positive predictive value, right? So, which, in other words, if I was tested positive, how likely I'm actually immune? So, in other words, it is. So, if you are test positive, so I have undertake a test. So the test says I'm positive. So how likely the probability? How likely I am indeed positive, right? So this is a more interesting question, right? So how likely you are immune to COVID-19 after you have done the test, right? Okay, so let's look at this issue Okay, so to answer that question, we need something called Bayes' theorem. So the Bayes theorem says that A conditional on B, A given B, the probability of A given B equals to this formula, as you can see this formula. So this is a probability of B given A. So A and B are two scenarios. For example, A could be A could be whether you are immune. Okay, you are immune, and the B could be the test positive. You are testing after you've done a test positive. A and PA is a probability of A itself. B is a probability of B itself. So this fundamentally it establishes how to use prior knowledge in analyzing data. So this is one of my favorite example of Bayesian intuition. So I think before I don't want to making these things more, very technical. So I think it's good idea to get some intuition. So this example is from an online course called Bayesian Methods for Machine Learning by this institute on Coursera. So this asks a question: a man is running. So when you look at the pictures, right? A man is running. Why? Why is man? You saw a man is running. So what's the reason? What's the explanation? So first possibility, he's in a hurry. Okay, the second possibility, he's doing sports. Third, he always runs. And four, he saw a dragon. So given this man is running, so what's the possible explanations? So here we can say this man is running is the data, is our observation, right? Then we have some prior knowledge. As I said, Bayes' theorem brings data and your prior information together, so to give you some conclusion from your data. So given the prior knowledge, we can exclude this number 4 option, right? Okay, because we know that it's very highly unlikely that there is dragon. Okay, the dragon doesn't exist, right? So based on this, we can basically based our prior knowledge, we can remove the exclude this option, this explanation. So based on data, we can probably decide whether it's the second scenario. So if we know that he's wearing sportswear, then probably he's doing sports, right? But if he's not wearing sportswear, then we say that probably he's not doing sports. Okay, let's say if he's not wearing sportswear, okay, we can remove this option. Now, similarly, whether he's in a hurry or he always runs, it depends on your prior knowledge. So if you know this person, he always runs, probably unlikely. But if you know this person well, then he seems always run from one place to another. Then he always runs. Probably this is the correct answer, or he just otherwise he could just in a hurry. Okay, so this tells us the importance of using your prior knowledge and your data to make a decision, right? So as in this example, prior knowledge tells us that a dragon doesn't exist, so we can exclude this scenario. Okay, so similarly, we can deal with this sports, whether he always runs. Okay, so let's get back to this formula for Bayes' theorem. let's suppose that A event is R plus, that you are indeed immune to the virus. B is test positive, which is that the test, the antibody tests predict that you are positive. So this formula tells you that what's the probability that you are positive given that the test result is positive. Okay, so if we're using this formula, we can calculate that probability, and it can be further shown that probability B, so this part, which is the probability of test positive, depends only on PA, which is prevalence, sensitivity, and specificity. And we also know that sensitivity and specificity are the fixed characteristic of tests, so it does not change in another population. That is why that when we see the papers, we usually see sensitivity and specificity. These are the two metrics that are usually reported, including the composite measures such as AUC for rho curve. So we are going to discuss that later. But the key point that sensitivity and specificity, they do not change in another population. So it is a fixed characteristic of the test. And so that means that given the test, the probability of A given B, in this case is a PPV, depends on the probability of A, which is the prevalence. Okay, so this formula established that the PPV depends on the prevalence. So if you want some, if you want some more formal equation to calculate PPV and MPV, so this is the equation. We can see that as I said, if you do this equation arrangement, you will get this formula eventually. But as I said, this is not a technical talk, so I won't get that into the details how this can be derived. But basically, we can see the PPV, which is probability. In this case, is a probability of you are positive, given the test result being positive, is it's a function of sensitivity, specificity, as well as the prevalence. Excuse me. Okay, so we can view the prevalence, which is PA, as prior knowledge, and test results is your data. So your data is test results, where the test results may predict you that you are positive or you are negative. So this is your data, and PA as prior knowledge. So why is it? The intuition is that if we know the prevalence is 0, then the probability of positive is always 0, regardless of test results. So you see, this is a kind of way to combine the prior knowledge with the data to give you a conclusion. So obviously, if we know that there's 0 prevalence in this population, for example, if we know that this is an isolated town or this is a isolated island, there has been no cases which has been isolated for a long time. There has been no case of COVID-19. Then the prevalence is 0. So if you bring the test kit to this island to get a test for someone, then regardless of the test results, we always know that the probability of you having been positive would be 0, right? So in this sense, we can view the PA, the prevalence, as a prior knowledge. The test results, on the other hand, can be considered as data. Then, based on this base rule, we can calculate the probability of positive given the test result is positive. Okay, to make the point, I also found this example I found online. So as you can see that you can do your own calculation afterwards. So the point is that given the same sensitivity and specificity, but with different prevalence, your PPV is quite different. So in this case, in the first case, 70%. In the second case, is 51%. Okay, so the prevalence, of course, is a huge factor for the PPV. So the takeaway message, the implication for this, that when you do the test, you need to have a good estimate of your prevalence. So in high prevalence places like for hospital workers or for bus drivers or other professions who may have high exposure to the virus, then the prevalence would be higher than other communities. So the test results for these people, this group of people, will be highly accurate, will be more accurate than other groups of people in the community. Okay, so the final point I want to make is taking a balance of different metrics. So the reason is that the performance metrics, one is not enough. Okay, so if you look at the fundamental table I showed previously, sensitivity, specificity, they often are considered jointly. Example is that if the test, for example, if a test always gives you positive results, then the true positive rate will be 100%, right? Which sounds wonderful, okay? But in that case, also which means that the true negative rate is 0%, okay? So what we want is some balanced metric or index, so to say, composite index to measure the overall performance. So we are not, only interested in true positive rate or true negative rate. We want some overall performance to be better. In that regards, we have a number of composite index to rank different tests. Okay, so let's look at some of the mostly commonly used composite index. So the first is the error under the ROC curve. ROC stands for receiver operating characteristic. Okay, so it may not make sense to you, but I believe this ROC curve, this thing comes from electric engineer. So it may have a bizarre name to you, but that's okay. The thing is that the AUC for the Tokner's test is it turns out it is average of sensitivity and specificity. Okay, so this equation is only relevant, okay, only applicable to 2x2 table. Okay, let me emphasize that this is only relevant to 2x2 table. Okay, it's not applicable to a continuous variable classifier. For example, if you have something like blood pressure or some continuous score, then you can also have this ROC curve, but they are not. They are different. It will be a different scenario than this equation does not apply. But for 2x2 table, it turns out AUC is the average of sensitivity and specificity. Okay, so it's really it's putting a balanced. So as a previous slide I just showed, you need to balance sensitivity and specificity. You don't want to have 100% sensitivity but 0 specificity. Okay. Another related index is this thing called Uden's J statistic. This is calculated by sensitivity plus specificity minus 1. So what we can see is that both AUC and J statistic contains this term sensitivity plus specificity. So if you are ranking if you have a number of candidate classifiers, if you are a number of, for example, you have a different antibody tests from testing products from different companies. If you want to rank, so which product is better, which is worse. So if you use AUC and J's, this J, Newton's J statistic, you get the same ranking, because so essentially it is using SE plus SP, sensitivity and specificity, as a ranking criteria. So another related, this F1 is called F1 score. So this is calculated as 2 times PPV times SE divided by PPV plus SE. So this is a useful score. I think it's quite often used in machine learning literature, but not in general. I haven't seen much of this use in general stats literature, but certainly it has some usage in machine learning literature. So another useful index is called Cohen's kappa. So many of you may be familiar with this term. So this term is used to measure the inter-rater agreement. For example, if you have one rater or one testing product, so you tell the patients whether you are positive or not positive. Then you have another product or another rater telling each patient whether you are positive or not positive. So we can also view this is a 2x2 table problem. Okay, you have two raters. Each rater gives you a yes or no answer, positive or not positive. So this is a 2x2 table as well. Cohen's kappa was originally used to measure how likely one rater is in agreement with another rater. Okay, but it turns out it is also a function of sensitivity, specificity, and PPV as well. Okay. Originally, I have to say that the original formula for Cohen's kappa is not as complicated as this one. Okay, it's a much simpler formula. But to demonstrate that the Cohen's kappa is also a function of sensitivity, specificity, and prevalence in the 2x2 table. So I'm also presenting this formula here. So that's the point. The Cohen's kappa can be just as with AUC J statistic F1 score. It is also a function of sensitivity, specificity, sometimes prevalence. This thing is a composite, taking a balance between all the metrics. So finally, I'm sure you are familiar with this thing called Pearson's correlation coefficient. Okay, I think many of you are already familiar with this. It turns out for the autonomous data, Pearson's correlation coefficient is also equivalent to Matthew's correlation coefficient. Okay, so I think this term, if you look at again in machine learning literature, is more common. It's more commonly referred to as MCC, okay, Matthew's correlation coefficient. But for the autonomous data, it can be shown that Pearson's correlation coefficient is equivalent to MCC, okay. So the formula for MCC can be expressed by true positive, true negative, false positive, and false negative as well. Okay, so if you want, you can also express this formula using sensitivity, specificity, PPV, etc. But the formula will be more complicated. But the point is that MCC can be also expressed as a combination of this fundamental table, these elements in the fundamental table I just showed you. in the first few slides, right? So this true positive, true negative, false positive, false negative. It is a composite index or score, if you wish, of these measures. And for the MCC is also happens to be equivalent to Pearson's correlation coefficient for a 2x2 table. So if you have a 2x2 table, right? So you can also use Pearson's correlation coefficient to calculate the correlations between the two measures. Okay, so I think that's the last slide. Thank you for watching. See you next time. Bye bye.